This is your friendly neighborhood physics teacher here, and we're going to talk about our Unit 4 free response questions on College Board. So there's 2 questions, and this is also our energy unit. This is our very first unit we did at the very beginning. So hopefully this is a review and we remember, but if not, I gotcha. We can go over this. So question number 1 states that this question is a long free response question. Show your work for each part of the question. And then it goes and shows like a little diagram. There's like 3 different not viewpoints, but 3 different sections of the diagram at different time intervals. So the first little diagram shows a rocket. Every time I say rocket, I think that the little Einstein song plays in my head. So it's saying that at the beginning we have a rocket. It's moving at initial velocity, and this is at time 0, so this is at the very beginning. And this is for rocket X. And it says it's being launched upward. Then we have a little snapshot of the rocket in the air. And this is at time t1, so this is at some time after it's been launched. And again, we're still dealing with rocket X, and this is when it reaches max height. We have another snapshot. Our little rocket is upside down now. And this is, again, some other time because this is at time t. Again, still dealing with rocket X. And this is when it reaches ground. So the rocket gets launched up, gets to max height, comes back down, and comes back down to Earth. And then it has a nice little paragraph explaining it. And of course, it's in AP terminology, so we're going to try to break it down to make things a little bit more easier. So it states, students conduct an experiment to study the motion of 2 toy rockets. In the first experiment, rocket X of mass mr, so all of these little rockets have little mass, or little mr masses, is launched vertically upward with an initial speed of v0 at time t equaling 0. The rocket continues upward until it reaches its maximum height at time t1. As the rocket travels upwards, frictional force is considered to be negligible. So that means there's no air resistance. Woohoo! The rocket then descends vertically downward until it reaches the ground at time t2. The figure above shows the toy rocket at different times of its flight. In the second experiment, which has not yet been conducted by the students, rocket Y has a mass of big mr, so for rocket Y, and rocket X, they're saying that the mass, and they're using big M for the rocket Y and little m for rocket X. They're saying that rocket Y's mass is bigger than rocket X. Will launch vertically upward in the initial speed of v0. So now they're saying that the oops. I meant that to do that a different color. Let's try that again. Little m and then v0. They're saying that the initial speeds are the same in both situations. At time t equaling 0 until it reaches its max height. Rocket Y will then descend vertically downward until it reaches the ground. So this too is what you should have gotten out of that little mini paragraph. So now it says 2 students in the group make predictions about the motion of rocket Y compared to that of rocket X. Their arguments are as follows. So this is just like our ranking questions when we had, student A, B, C, D with weird names, y'all all said. And you had to sit there and say which one was right, which one was wrong, and why, and all that stuff. So it's just those questions, but except it's still dealing with like 4 students. You only have to do with 2, so not that bad. So student 1 states. So this is dealing with student 1. So it states that rocket Y will have a smaller maximum vertical displacement. So it's saying that the Y will have so it says that rocket Y will have a smaller maximum vertical displacement than rocket X. So it's saying rocket Y won't go as high as rocket X. Although it is launched upward with the same speed as rocket X and has more kinetic energy than rocket X. So they've stated that kinetic energy has more kinetic energy than rocket X. And I have that flipped. There we go. Because rocket Y will have a smaller maximum vertical displacement than rocket X, I predict that it will take less time for rocket Y to reach the ground compared to rocket X. So now they're saying that rocket Y will have less time than rocket X. So we need to check to see if this is right. So we're going to look at the height, we're going to look at the kinetic energy, and then we're going to look at the time. So if we look at the height, so the equation that we're going to look at is our y equals y naught plus v y naught t plus 1/2 ay t squared. So we know that y is going to be our max height. Y naught is just going to be 0 because we're starting at 0 height. We know our initial velocity. We don't know our time. And our acceleration to y is just gravity. So this variable and this variable are the same. So if we were going to, here, let me rewrite this. So let's look at it like this. So this is for y. So if we have y equals, we know y naught 0, so we're not going to worry about that. So vy naught t plus 1/2 gt squared. And we want to compare that to the equation for our x, rocket x. It's the same equation, we're just comparing the two. So we know that our v naughts are the same. We know that. And we know that our gravity is the same. But that still leaves us with 2 unknowns, our height and our time. So that right now this equation doesn't really help us, but we can come back to it. But let's look at our kinetic energy equation. So our kinetic energy equation is K equals 1/2 mv squared. Our velocities are still the same, but our masses are not. For our y, our rocket y, our masses is greater than compared to our mass in rocket X. So your mass and your kinetic energy are direct relationship. So as your mass increases, your kinetic energy is going to increase. So this is saying that your kinetic energy for rocket Y is going to be greater than your kinetic energy for rocket X. And that's what student 1 said. So that one is correct. So we know that part's correct. We're still working on the other two. So now let's look at time. Dealing with time, we can use our final velocity equals initial velocity plus AT, but again, we're in the Y direction, so our A is going to be gravity. We're going to use the exact same equation for the Y direction. We know that our initial velocity is the same, because it says it. We know gravity is the same, because guess what? We're still on Earth. We're not on Mars yet. And our final velocity would just be when it hits the ground. That's going to be 0. That's going to be the same, because guess what? They both hit the ground. So if your final velocity is the same, your initial velocity is the same, your gravity, your acceleration due to gravity is the same, guess what that means for your time? Your time has to be the same also. So time on the rocket on Y has to equal the time on rocket X. They said that time would be shorter, so that was wrong. So now that we know that time is the same, if we go back up here, we now know that time is the same. So guess what that means for your height? It's the same. So again, saying that your height will be less is wrong. So student 1 the only correct statement they made is dealing with kinetic energy. Their height explanation and their time explanation is wrong. So now let's go to student 2 and see what they say. Student 2 states, rocket Y will have the same maximum vertical displacement as rocket X because both rockets have the same kinetic energy. Since both rockets will have the same maximum vertical displacement, I predict that it will take both rockets the same amount of time that reaches the ground. Okay, so again, we're kind of breaking it down. So the first thing that student 2 says that it'll have the same vertical displacement. So it says that heights are going to be the same, which we already did some figuring out, which is a correct statement. Another thing that they say that they're going to both have the same kinetic energy. Well, what we did up here is we stated that the kinetic energy of rocket Y would be more than rocket X because rocket Y has more mass. So student 2 is wrong stating that the kinetic energies are going to be the same. And then it says, since both rockets will have the same maximum vertical height, I predict that it will take both rockets the same amount of time to reach. And that is correct also. That height and time go hand in hand. Height tells you, or time tells you the height, or vice versa, height tells you the time. So that's correct. So if you notice, they're kind of flip-flopped. Student 1 was right about kinetic energy, but wrong with distance and time. Student 2 was wrong about kinetic energy, but right with about distance and time. So they're kind of flip-flopped. So now that we broke down student 1, student 2, let's see what the question says. It says A, for part A, ignore whether the student's predictions were correct or incorrect. Do not simply repeat the student's arguments as your answer. So I, which aspect of student 1's reasoning, if any, are correct? Explain your answer. So looking at student 1 had one reasoning that was correct, and that was the kinetic energy. So you would say student 1, so this would you need to put in maybe three sentences or so. So you could say that student 1's prediction about kinetic energy was correct. rocket Y, it will be greater than rocket X because mass and kinetic energy have a direct relationship. So since rocket Y has a greater mass than rocket X, that means rocket Y will have a greater kinetic energy than rocket X. And if you want to throw in some equations in the mix to show that, kind of like I did here, that'd be a good explanation. But if you say explain, make sure you throw some words in there too. Don't just, you can use equations to help explain, but they need some wordage. That's a word now, just go with it. You need some words in there to explain it also. Part 2 says which aspect of student 1's reasoning was incorrect. Well, that'd be your Y and your time was incorrect. Again, it says and why. So student 1's reasoning about the vertical displacement and time were incorrect. Mass does not affect your height at all, and therefore, since it moved at the same height, it's going to take the same time. And then again, you could throw some equations in there to explain. Triple I states which aspect of students 2 reasoning, if any, were correct. Well, their reasoning for height and time were correct. Again, you give your little explanations with the equations. And then which aspects of student 2's reasoning, if any, were incorrect, would be the kinetic energy. And again, you can give the equations and how mass affects it. Little explanation there. So just sitting there and breaking down, so we answered the questions even before it asked us, just because we knew we were going to have to sit there and compare. So breaking down student 1, student 2 information before you even answer the questions might give you a clear mind on being able to answer the questions easier. Incorrect. We already did that. Okay. So B. So this was all part A. So part B states using quantity reasoning. So anytime it says quantitative reasoning, you're going to end up using equations. So using quantitative reasoning, including equations as needed. Oh, well, there you go. To derive expressions for the maximum height achieved by rocket X and rocket Y. Express your answer in terms of V naught, little mr, big mr, g, and or other functional constants as appropriate. So we're now going to be deriving equations. Yay! So basically, it's one. So again, so if we kind of get through the, let's break down what exactly B is asking for. It's wanting you to find max height. Okay. So for B, we're looking for max height. So we're looking for Y, and our equation can only have V naught, little mr, big mr, and g, and any other constants. So that'd be like if it needed a theta or a mu or something like that. Now, if you're looking for velocity, masses, and gravities, we can't use our 1D motion equations like we kind of did up here. That doesn't work. So we know we can't use that equation. Hopefully, when you see velocity and masses and gravity, you think energy. So we got to use our energy equations. So we got to think about what our initial total energy and our final total energy. We got to compare the two. And we got to do this both for actually, the equations are going to be the same. So it says we need to do both for your rocket X and rocket Y. It's going to be the same equation, just your masses might look a little different. So you have to think about what energies happen at the beginning, what energies happen at the end. So let's go back to our drawing. Zoom in here. Whew. So we're just worrying about beginning and end. We're not necessarily worrying about stuff in we're trying to find max height. So we do have to worry about the stuff in the middle. So we're just going to we're just going to go from beginning to the maximum height. We're not worrying about the end. So what type of energy is happening at the beginning? Well, hopefully you're noticing there's no height, so there's no gravitational potential, and it's moving, so there's kinetic. Woohoo! So there's only really kinetic energy at the beginning. At the end, it reaches its max height. It's not moving anymore. It's just kind of chilling there before it falls down. So that would be your gravitational potential. So your energy at the beginning is going to be kinetic energy. Your energy at the end is going to be your gravitational. You break down those equations, so 1/2 mv squared, and that's m naught. And if we're doing, let's worry about x first. So mr, little mr, equals mass times gravity times your final velocity. So that would be mr, not final velocity, your height. Woo, what did I say velocity? I meant height. Mr, g, and then your maximum height. So we need to get maximum height by itself. So we're going to ahead and divide by this. Guess what happens to your masses? They cancel. That's why mass doesn't matter. And you have your V naught squared divided by 2g equals your maximum height. So there we go. Okay. So there we go. That's our max height. And guess what? You only have to do it once because the masses cancel. Mass doesn't matter. So this is why max height is max height regardless if it's a big rocket or a little rocket. It's being launched at the same velocity and you're on the same planet, you're going to get the same max height. So we have to do it once. Yay! So let's look at part C now. Part C states, using quantitative reasoning, we're doing another equation? Okay. Includes equations as needed to derive expressions for the time it takes rocket X and rocket Y to reach the ground after reaching their relative max heights, height X and height Y. Express your answer in terms of V naught, little mr, big MR, Hx, Hy, gravity, and other fundamental constants as appropriate. So now we're looking for time. So now we're looking for time. And the only variables we're allowed to use is V naught, little mr, big MR, Hx, Hy. That's just dealing the height of your X, height of your Y, and then G. So those are the only ones we're allowed to use. So we're going to go back to this equation up here that we tried to use for our time. Now, how I knew to use that equation? Because not very many equations have time in the mix. Mostly it's just our 1D motion equations. We can't use the equation we used for time up here because there's no way to get rid of our velocities. So our V final, yes, is 0, but we can't get rid of that V initial, and that's not one of the ones we can use. But here, we can actually get rid of our initial velocity, and I'll show why. If you remember, dealing with, because it says starting at height, going down. At the very, 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 very tippy top, of your projectile. Your velocity is 0 up here. So if we're just dealing with, if we're ignoring this part, I can erase it. Erase. Yeah. There we go. If we're just dealing with this part, that becomes our initial velocity. That becomes our initial velocity. So we can do our y equals y naught plus v y naught t plus 1/2 ay t squared. And now we just plug in for what the equations are. So if we're dealing with x again, so that would, our height would be hx. That is just 0. That is now 0 times t plus 1/2, that'd be gravity, times t squared. So now that just leaves us with hx equals 1/2 g t squared. We need t by itself, so we're going to go ahead and multiply both sides by 2. And then we're going to divide both sides by gravity. And then we need to get rid of that squared. To get rid of a squared, you're going to square root. So you get your time is the square root of 2hx over g. And you get to do that all over again for your y. You don't necessarily have to show all the work again, but just show that 2 by gravity. So this is why your time is the same. Woohoo! We derived another expression. So part D. Part D states that explain how any correct aspect of the student's reasoning identified in part A are expressed in your mathematical relationships. So we got to go to part A, back to part A. Part A deals with energy. So he was right about kinetic energy. So that's where the part C basically when we derived. So since it has the same kinetic energy, and so therefore it has the same height, it's the same gravitational. So you're just stating, so basically, an example would be because rocket Y has a greater mass than rocket X, both rockets are launched with the same initial speed, and so your kinetic energy of rocket Y has more kinetic energy than rocket X. However, when conservation of energy is applied to the rocket Earth system, the masses cancel, meaning the masses of the rocket do not affect the final height that is reached by each rocket. So there you go. So you're just saying, yes, this part was correct because of this. Part DII says, explain how any correct aspects of each student's reasoning affected part A are expressed by your mathematical terms. So now this is when you're dealing with the time. So because both rockets will experience the same acceleration and both rockets each have the same maximum height, therefore they will take the same amount of time to reach the ground. So you're just combining part A with part C and B and just putting it into words. Part C and B and C, you're doing mathematically. Now you're just putting it into words in part D. Okay, second question. Dun-dun-dun-dun. So second question states, this question is a short free response question. Show your work for each part of the question. And you have 2 diagrams now. And this diagram should look very similar because we did a lab like this. You have a platform, and then you have a person jumping, and it says that's platform. It says that this distance is d. And it says that's the chord. Okay? And it says this is the initial state. Then it gives you another situation. Still says that this is distance d. This is still the platform. But now the person is all the way down here. And that's still the chord. And it says that this and this is H. And this is the final state. So you see two snapshots. You see right when the person's jumping with the bungee cord, and you see when the person at the end where he gets to the bottom. Then it says, an amusement park ride is designed such that one end of elastic cord is fixed to the platform that is a distance d above the ground. The other end of the cord is attached to a person of mass m. The cord has an unstretched length of L. To begin this ride, the person jumps up from the platform with initial speed v, as shown in figure 1. As the person falls, the elastic cord stretches, and can be modeled much like a spring of negligible mass. After the cord can no longer be stretched, the person is a distance h above the ground and is no longer in motion, as shown in figure 2. The reference point for zero gravitational potential energy is the person cord Earth system as a distance h above the ground. All frictional forces are considered to be negligible. So basically, what it's saying is right here, you're pretending like it. So your gravitational potential equals 0 right there. Is basically what it's saying. That's probably the little bit that confused you. Because I had to read it a couple of times. The initial state of the system is shown in figure 1, and the final state of the system is shown in figure 2. AI. Describe the energy transformation that takes place from the initial state to the final state of the system. For each form of energy, identify the object or system that has that form of energy. Okay. So the person's moving, right? So at the beginning, the person's moving. So we have to think about, here we'll make energy at the beginning equal energy at the end. So we need to think what type of energy is happening here. So at the beginning, it has kinetic energy. And gravitational potential energy, because we have some height. Moving and has some height. There we go. But the cord hasn't started stretching yet, so we don't have our elastic potential. At the bottom, we have, it's not moving, it's saying we don't have any gravitational, but it's completely stretched out. So now we have our potential, spring potential energy. So that's kind of what's happening here. So you could, write your little equation, but make sure it says state, so make sure you put some words in there. So you can say, like, at the beginning, the person has kinetic energy because the person has an initial velocity, and the person cord Earth system. So we have the person, the cord, and the Earth are all playing a part, has gravitational potential and kinetic energy. Because the person's moving, so we have to take the person into consideration, the ground, because that's what's pulling it down, that's our gravity, and then the cord, because that's what's eventually going to stretch. So then for our final, so at the end, the person cord Earth system has a spring potential energy, the person has no mechanical energy because it's not moving anymore. So basically you can write this equation, but then you need to explain it and say that it's the person, cord, earth system. The reason you know it's all three is because the person's moving, that's where the kinetic energy. Gravitational, the earth has to play a part because of gravity, and then the cord has to play a part because that's the spring. So it's the earth, the cord, person, cord, earth system. So that's for part 1. Part 2 says derive an expression for the spring constant cord in terms of D, L, H, V naught, M, and any physical so this was for I. So now let's do this for double I. And it's saying that we're looking for our spring constant. So remember that's little k. And we want it in terms of D, L, H, V naught, M, and any physical constant. So that'd be like G. So we kind of already started the equation already. So we're going to just be using this right here. So we're going to rewrite it real quick. So we have our kinetic energy plus our gravitational potential energy equals our spring potential. So our K is just 1/2 mv squared. Our gravitational is just mgy. And our spring is 1/2 little k x squared. And now we just need to break down which each one of these things are because we don't want a lot of these. Kinetic energy pretty much can stay the same because 1/2 mass, just add a little naught to your V. Woohoo! That one's set. For your gravitational, mass and gravity can stay, but Y can't. Y is your height. So now we have to go up here and figure out what Y would equal. So Y is how high, or pretty much how tall the person's jumping. Now the key thing is, a lot of people just want to throw D in there. Well, the platform's at D, so they jumped at D. But this is AP, it can't be that easy, right? It's stated that your zero gravitational happens at H. So in this case, because of that, hold on. No, too high. Because of that, our Y is going to end up equaling D minus your H. D minus your H, because that's how far the person actually falls. So we're just going to put D minus H there. That H should be capital H, not little h. Okay. Then equals 1/2 our spring constant. It needs to be a little k. It's so hard to draw little k's versus big K. And then our X. X, remember, is how much the cord stretched. How much the cord stretched. So remember the cord length was L. So the cord length is L. So we know that the person fell D minus H, but to know how much the cord actually stretched, we're actually going to have to do Y minus L, which ends up being D minus H minus L, to figure out how far, to figure out our X. So remember, X is pretty much how far it was displaced. To know how much it stretched, you got to compare how much the person fell compared to the original length of the cord. Because if you think of anything, your cord length is like this, if it's just hanging there. And go back and remember the bungee cord, Barbie bungee cord lab. So when you put all your rubber bands together, it was certain length. But as Barbie or Iron Man or whatever you used fell, it kind of stretched out. So basically what X is that. So if the normal length is L, and then how much the person fell was our Y, and our Y equals D minus H, actually that's why you're doing D minus H minus L for X. Let's see, it's not letting me shrink it. Okay, fine. D minus H minus L squared. Whew, fun stuff. So now we're just trying to get K by itself. We're going to go ahead and divide both sides by D minus H minus L. D minus H minus L squared. Don't forget the squared. So we get 1/2 mv naught squared plus mg D minus H divided by D minus H minus L squared equals 1/2 little k. Well, we need that 1/2 to go away, so we're just going to multiply both sides by 2. And so that 2 causes 1/2 to go, so that goes there. So we get mass times V naught squared plus 2 mg D minus H divided by D minus H minus L squared equals, equals our spring constant. So the trickiest part here is realizing, honestly, our X, our stretch. Because a lot of people forget about the length of the cord is L. So a lot of people forget about that. So that's what throws a lot of people off on that one. And so that's the second question. So part B. Part B asks, suppose that air resistance cannot be ignored. For the position at which the person has jumped from the platform and the cord reaches its maximum stretch length, how does the stretch length of the cord in the case with air resistance compare with the stretch length in the case in which air resistance is ignored? And it's just wanting you to briefly explain. And so a little example of that would be after the person jumps and falls to the ground, a force of friction will be exerted on the person from the air. The kinetic energy of the person will be converted into the form of non-mechanical energy due to the non-conservative force of friction. So basically, if you're looking at our equation up here, so it'd be kinetic energy plus our gravitational subtracted by work due to friction. Okay, because friction would be working against the energy. Therefore, the mechanical energy of the system decreases as the force of friction is exerted on the person. With less mechanical energy available in the person cord earth system, there will be less mechanical energy that can be converted into elastic spring potential. Thus, the cord will not stretch as far as the case without air resistance. So you can think about equation-wise, and you could write down this equation to help explain that frictional force would be doing negative work because it's going against the system. And since it's a person cord earth system, air is not part of the system, so that's adding an outside force. That's what it meant by a non-mechanical energy or a non-conservative force, because that's a force that's outside the system affecting it. So it's taking that work away. So there we go. So that is your part 4. If you have any questions, please let me know. Remember, you are loved and appreciated. Bye.